Coming up on Quest, how the wines we drink could change as the climate warms.
Trying to look at their adaptability to hotter temperatures.
What we can learn from tsunamis of the past to protect ourselves in the future.
You can estimate when that area might be hit again.
A high-tech tool that maps hidden sources of water. And an artist who brings the beauty of botany to life. Next on Quest.
Support for Quest is provided by the National Science Foundation, the David B. Gold Foundation, the S.D. Bechtel Jr. Foundation, the Dirk and Charlene Capsonell Foundation, the Vadez Family Foundation, George G. and Jeanette A. Stewart Charitable Trust, and the members of KQED. Quest is a project of KQED Science.
It's believed that Pinot Noir is 2,000 years old. It's thought that it was described by some of the Romans who came to Gaul, France, in the 1st century.
If you've ever asked a winery owner to talk about his wine of choice, you're likely to have been treated to a rapturous ode.
What I like about it is that it's challenging, it's subtle, but when it's good, it's really good. So it's sort of worth the struggle.
What you're less likely to have heard is that global warming could pose a threat to cool climate grapes like the esteemed Pinot Noir.
It's really a very special grape. It doesn't flourish in a lot of climates. It's not a very forgiving grape. It tends to like cooler spots.
David Graves began his pursuit of the perfect Pinot Noir in 1981 at Saintsbury, the winery he co-owns in Napa's Carneros region. The marine fog that enters the bay blankets Carneros and makes it an ideal place to grow good Pinot Noir. But if some climate researchers' predictions come true, by the end of this century, vintners might not be able to grow Pinot Noir in Napa Valley.
Perhaps in downtown San Francisco or Golden Gate Park, for instance, the Berkeley Hills, all areas that are really probably too cold for viticulture now. If it got dramatically warmer, those might be the last places you could grow the cool climate varieties.
If you think that's far-fetched, consider this. Researchers from Stanford and other universities estimate that by 2040, global warming is likely to cut in half the area in Napa and Sonoma Valleys suitable to grow any top-quality wine grapes. And by the end of the century, New England and the Pacific Northwest could be warm enough to make premium wines of their own. It's a fact of chemistry. To produce good wine, you just can't have extreme heat or extreme cold. As grapes grow and ripen, they need heat, followed by a cooling off period. The heat produces the sugars that will become alcohol. The cooling slows this process long enough for the compounds that produce the flavors in wine to develop. Temperatures above 95 degrees without subsequent cooling degrade compounds called anthocyanins, which give red wines their deep color and contribute to their complex flavors.
As temperatures increase, the anthocyanins are impacted negatively. Their chemical structure, the way their bonds are formed, actually split and fall apart. Those chemical elements are literally dropping out of the wine and going from a darker color to lighter colors.
What happens in Napa and Sonoma Valleys is important because their high-priced grapes contribute close to half of the value of California's $2.2 billion a year wine grape harvest. But the exact impact of climate change is difficult to predict. As California's interior warms up, the heat could pull in cool air from the ocean, like a giant vacuum cleaner.
It may actually get too cold to grow grapes in some of the regions that we now consider our cool regions because of greater amounts of fog, greater amounts of cold air being pulled in through the Golden Gate, for instance, into the Central Valley.
What researchers do know is that one of global warming's most daunting challenges for California farmers is water availability. The Sierra Nevada snowpack, which fills reservoirs every summer, already has begun to melt earlier each year. And state hydrologists say it could decline 90% by 2100. To deal with water scarcity, David Graves and farmers around California are collecting rainwater to use in times of drought. They're also using technology to determine precisely when to irrigate and how much. But at the University of California, Davis, researchers are preparing for a completely different scenario. They're looking at varieties that could replace the cool climate Pinot Noirs and Chardonnays of today.
This is a collection of unusual varieties, at least unusual to California, that are somewhat more designed for warmer climates. This is Marsanne from the south of France in the Rhone region. It's a white grape. We have it growing here. Most of these warmer climate varieties we're looking at are white varieties, trying to look at their adaptability to hotter temperatures. Then we have some Torrontes, which is a Spanish grape grown widely in Argentina. We have some wines for that to show you today.
Torrontes is not your parents' wine, unless that is, your parents are from Spain or Argentina. But it could very well turn out to be your children's wine.
Well, the first wine, Torrontes is...
Welcome to the wine tasting of the future.
This wine has very aromatic characters in the bouquet and some citrus and grapefruit characters, and it has a nice spicy finish.
It takes 3 to 4 years before a vine starts to produce grapes, so replacing varieties is a big investment for winemakers. And new varieties present other challenges. Say you find this spicy new white wine on the wine list. Do you know how to pronounce its name?
This wine, we say in Spanish, we call it Torrontes. You emphasize, you put the stress on the last syllable, Torrontes.
Well, let's try the second wine. Okay. Verdelho is very much different than your Chardonnay, Sauvignon Blanc, and Pinot Grigio. It has some grassy characters to it.
Nice aromatic characters both in the mouth and the nose. Chardonnay, Sauvignon Blanc, Cabernet, Merlot, the wines we know as international varieties, those have really been marketed well and accepted well around the world. It's easier to sell those wines. It's easier for people to know them and understand them and purchase them too.
That's why California's production of the well-established Pinot Noir quadrupled from 2003 to 2013. Growers have even planted this cool climate grape in the hot Central Valley. At the same time, large wine companies have started investigating the possibility of cultivating warm climate varieties new to California. One of the world's largest wine and beer companies, Constellation Brands, is collaborating with UC Davis on this research. California's wine growers, large and small, are preparing for the vineyard of the future.
You need to be very flexible about your approach. You need to look very far and wide for varieties that may be successful in the climates of 2080. You need to be very skillful at adapting to changing conditions. You have to be very skillful at adopting new technologies. It's pretty clear that change is the constant in this whole thing.
December 26, 2004. A massive tsunami is set on a collision course across the Indian Ocean. When it slams into the coastline, the force of the wave wipes entire communities off the map. Even today, it's hard to comprehend the sheer devastation.
In Indonesia, 150,000 or so people lost their lives. Even in Sri Lanka, which was more than 1,000 miles away, there were 36,000 people who lost their life. All told, almost 250,000 people.
Bruce Jaffe is a tsunami expert at the U.S. Geological Survey in Santa Cruz, California. Soon after the waters receded, Jaffe and his team traveled to Indonesia to study the aftermath with the hope of better understanding when and where other big tsunamis may occur. Tsunamis are waves generated by abrupt vertical movement of the sea floor caused by earthquakes, volcanic eruptions, landslides, or even an asteroid impact. This animation shows the birth of the 2004 tsunami with a magnitude 9.1 earthquake deep within the ocean floor off Indonesia.
Here the earthquake is propagating, and then when you put the water on it, all the water does is mimic the deformation on the seafloor. That creates the tsunami wave.
In some places, the resulting wave reaches 100 feet high when it strikes land.
This video is taken in Banda Aceh, the capital of the Aceh province of Sumatra. The tsunami was maybe 30 feet high. In the other parts of Sumatra to the south, the tsunami was 100 feet high.
Since the Sumatra tsunami, several others have wreaked havoc. This dramatic footage graphically illustrates the devastating power of the tsunami that hit after the 2011 Japan earthquake. The tsunami killed 16,000 people and caused a meltdown at the Fukushima nuclear power plant. Tsunami waves raced across the Pacific Ocean and hit California's coast 9 hours later. The surging water caused more than $50 million of damage to 6 counties, including Santa Cruz, where the force of the waves smashed docks and boats. In response to recent tsunamis, the California Geological Survey and State Office of Emergency Services partnered with the federal government to create new maps that model the potential strength and flooding from tsunamis. These playbooks may help minimize damage to California harbors and help coastal communities update their evacuation plans. To prepare for tsunamis, it also helps to study the clues they leave behind, which scientists can use to trace their origins and estimate when they may strike again.
After the water has gone away, the sand is left behind. And so it's a record, it's a calling card, if you will, of the tsunami.
Big tsunamis throw tons of sediment onto shore. The larger grains of sand settle first, with the lighter sediment coming to rest after. This creates a sand layer that leaves a telltale tsunami fingerprint.
When you find multiple deposits that were formed many years apart, you can start looking at what the hazard is in an area, estimating on when that area might be hit again.
Since a major tsunami may only strike an area every few hundred years, studying these sand deposits can help spot possible hazard areas with little or no recorded tsunami history. Good places to investigate are geologically active regions such as the Pacific coast of North America.
The Pacific is sort of one big hotspot. We've got trenches almost completely around the Pacific, and it has to do with plate boundaries.
For hundreds of millions of years, the plates, or rocky slabs that make up the Earth's outer crust, known as the lithosphere, have moved around the globe in a process called plate tectonics. Over time, the pulling apart and crashing together of plates form the continents and oceans, as well as island chains, mountain ranges, and other features around the globe. Sometimes, when two plates collide, one is pushed under the other, creating areas called subduction zones. Normally, plates move just centimeters per year, but occasionally they move rapidly in one large snap. This violent movement creates big earthquakes.
If you look at what happened in the Indian Ocean, it was 600 miles long and 200 miles deep, though that whole slab has to rip and break. One slab, pulling the other slab down, it rebounds, huge amount of energy. That's a lot of water to displace.
It's hard to plan for an event that may only happen once every 300 years, but the State Office of Emergency Services and NOAA, the National Oceanic and Atmospheric Administration, have established tsunami hazard zones along the California coast. More than 6,000 tsunami hazard signs posted in coastal areas help direct residents to higher ground.
Tsunamis do occur along the coast here. San Francisco, we've had them in the bay. So yes, they are a real threat. They are rare to have damaging tsunamis, but when they do occur, those damaging tsunamis can be devastating. So a warning system in place is very necessary.
The warning system starts with NOAA's Deep Ocean Assessment and Reporting of Tsunamis program, or DART.
What we have here is the DART system, the buoy that sits on top of the water. You have the pressure sensor that will measure the pressure of the water above it. If it picks up a long period wave, being a possible tsunami, it will then transmit the information to this buoy. The buoy will then send it to a satellite, and then the satellite sends it to the warning centers.
After the 2004 Sumatra tsunami, NOAA expanded the DART program from 6 to 39 buoy stations in the Atlantic and Pacific Oceans. Although the system has been hampered at times by malfunctions, it's designed to measure signs of tsunami waves and relay the data to warning centers in Hawaii and Alaska.
Now, a tsunami will actually travel at hundreds of miles per hour. When a warning is issued, or if you feel an earthquake that knocks you off your feet, you need to get away from the coast. You need to go inland into higher ground.
Even if major tsunamis off the coast of California are rare, the damage they can cause requires constant vigilance.
Nature is very powerful, and we have to respect it. If we don't respect it, that's when it comes and gets us.
My name is Candace Elliot. My job is illustrating the science of botany, which means drawing illustrations for publishing in scientific journals, drawing beautiful flowers, and making posters for our laboratories. Biological sciences have been traditionally visual. We've had pictures of animals, plants. You can't really describe it in words, you have to have a picture. When I started, all this sort of thing was done with pens and pencils, things like that. Now it's all electronic. It's the same thing. You're sitting there, you're drawing with pixels instead of liquid media. I started with a photo. I see what I want out of this picture. I want the mushroom. And then I can take a couple of tools, lighten up the light parts, darken the dark parts, so you have that enhanced contrast, because the camera doesn't get that contrasty stuff. It's introducing a little bit of this sort of indescribable feel of a painting as opposed to a photograph. I think something inside of us realizes this is not real, but more real. It's like it's standing up saying, here I am, you know, with the hat, the cane, big smile, saying, look at me, because I'm gorgeous. Biological illustration talks to people in the same way that professors that have a way of making you excited about a science, they can do it verbally, I can do it visually, and that's what I've been trying to do.
Fly across almost any landscape in the country, and you're likely to see traces of water sources that seem unconnected. Rivers and streams, lakes and ponds. But beyond what you can view is a far richer network of underground sources called aquifers that provide fresh water for drinking, agriculture, and other critical needs. Finding these sources is tricky, but you can see clues to these water deposits that most of us depend upon for survival.
It's difficult to see an aquifer. Aquifers are saturated materials. We stand on top of the land surface, the aquifers are below us, so aquifers and groundwater become an act of faith. You have to believe that those materials below the land surface are in fact saturated.
Aquifers form when rain or surface water seeps below the ground, filling small spaces between sands and gravels, creating water-soaked sediments that can be extracted by wells.
Outcrops like this give us an idea of what the aquifers are like below the land surface. Oftentimes we wonder where the water is, and we can come to this point where you can go down and stand on that groundwater as it becomes surface water.
But elsewhere, the connection between surface and groundwater is far from clear. Beneath the Great Plains is one of the world's largest aquifers, stretching from the Dakotas to Texas. But other regions contain only a patchwork of aquifers, so locating them is no easy task. And as more states cope with ongoing drought and surface water from rain and snowmelt dwindles, it's become critically important for leaders of natural resource districts to map and manage groundwater reserves.
This goes
Correct.
south, this goes north.
Yeah.
Exactly.
Today, managers of the Lower Platte South River Basin are meeting geologists from Exploration Resources International to locate aquifers in their region.
So we connect the dots, we make a three-dimensional image, and we come up with a volume of the aquifer.
This study will answer how large are the aquifers, how are they connected to rivers and streams and lakes, and how much water is in storage. That's the goals.
Traditionally, geologists have relied upon one costly and time-consuming method to find aquifers.
When we drill test holes, we're concerned about the character of the materials that store and transmit water. It's got sands and gravels and silts and clays. Depending on where you are, it can be just about anything.
And that's a challenge because test holes are usually drilled between great distances, every 3 to 6 miles. By analyzing samples layer by layer from each drill hole, geologists can map the water-bearing sands and gravels that form aquifers. But since the drill holes are so far apart, they can only estimate the shape of an aquifer between each site.
And then we would take a whole group of these drill holes and we would use our imagination and our training to fill in the dots.
Go on the next slide. You can.
For 150 years, geologists have been doing it with our imagination. Now we've got a new tool that helps fill in the blanks.
The new tool is called SkyTem. SkyTem is an airborne geographical survey system used around the globe to measure aquifers electronically.
The structure looks rather fragile, but it's very robust. It is built out of non-metallic materials because the system that we use sees metal. So we want to minimize the metal that's in it. Attached to the platform, on the front end of it, is a magnetometer, and it measures the background of that particular site of what the Earth's magnetic field is doing. On the entire loop around the outside is a series of wound copper wires, and that's the transmitter. That's what sends the signal into the ground. All the helicopter is the vehicle that carries this. Everything is just quick clip to the bottom of the helicopter and off it goes. It flies at approximately 50 miles an hour, 100 feet off the ground. The helicopter will be 100 foot above that.
SkyTem data can help natural resource districts identify, protect, and conserve water supplies to serve the needs of local populations.
What we would like to see is aquifer everywhere. We want water for everyone, every place. That's not the way it works. The aquifers are very limited in size and scope. Some of them can be many tens of miles long, and some of them are maybe a quarter of a mile around. It's hard to imagine how these aquifers interact. They may be totally disconnected, or they may be very connected. We don't know that until we do this mapping.
As the rig flies back and forth along parallel lines, SkyTem shoots rapid-fire radio waves into the ground every 9 feet, to a depth of 900 feet, all the way to bedrock.
It basically sends a radio signal into the ground. The rocks feel that radio signal and then kind of get a little energy and send energy back out. It says, I'm a sandstone, or I'm a sand and gravel body, or I'm clay and silt. Well, that's what we're mapping. Is it electrically conductive, or is it electrically resistive? So the aquifer material is resistive. So that's what we want to see if you want to know where the aquifer is. If it's electrically conductive, that's the clays and silts. It's like what you would use with silly putty. Not much water gets through that. So that tells us where the aquifer isn't. Between those two, we map that difference and we make a map of where everything is.
Each SkyTem signal acts as a virtual borehole that displays sediments in vivid colors. For geologists, blue and green mark water-resistant silts and clays, while yellow and red reveal the sands and gravels that make up aquifers.
When it's all done, you will look at a picture sideways through that map. You will be able to see what geologists always want to see. We want to know what's real. We want to know where our imagination is and where the reality is. The important part is when we're mapping, we know the difference between where we have aquifer material and where we don't.
Support for Quest is provided by the National Science Foundation, the David B. Gold Foundation, the S.D. Bechtel Jr. Foundation, the Dirk and Charlene Capsonell Foundation, the Vadez Family Foundation, George G. and Jeanette A. Stewart Charitable Trust, and the members of KQED. Quest is a project of KQED Science.